Yeah, welcome to Electrical Machine 1 lecture. In the previous lecture, we have discussed the characteristic of DC shunt generator. Today, we are going to discuss the characteristic of DC compound generator. But the DC compound generator is dominantly DC shunt generator. Therefore, the characteristic of DC shunt generator is much more similar to the characteristic of DC shunt generator. So now we will see the compound generator. There are two types of compound generator. One is the cumulative compound generator and second is the differential compound generator. So in case of cumulative compound generator, the flux produced by series field winding, flux produced in series field winding and flux produced in the shunt field windings, either they are additive or subtractive. If the flux produced by shunt field winding and flux produced by series field windings are additive in nature, then it is called as a cumulative compound generator. And if the flux produced by the series field winding is opposite to the shunt field winding, then it is called as a differential compound generator. Now, in this circuit, this is the DC shunt field current and this is the series field winding. This series field winding is connected in series with the load. So the current in the series field winding is the function of load. As the load is small, the current in the series field winding will be small. This is the terminal A1, positive terminal, negative terminal is A2. Similarly, F1, F2, and the series field terminal S1 and S2. So here A1 is connected to S1 and this is the cumulative compound generator. But if you want to make the differential compound generator, we have to reverse the current in the series field winding. So in this diagram, the current direction has been reversed because your S1 is as it is S2, whereas the current is going to flow in this direction. Means from A1 is connected to S2, so the current direction will be opposite as compared to the previous one. So in this way, it is a differential compound generator and earlier is the cumulative compound generator. Now this can be explained with the help of this diagram. That is, this is the pole shoes and pole core is there, where we have carried out the shunt field winding and series field winding. Earlier, the current in the shunt field winding and series field winding are in same direction. Current in the same direction as it is given in this diagram. The current in the shunt field winding and current in the series field winding both are in same direction. Therefore, the flux produced by shunt field current ISH and the flux produced by series field current phi SE both are in the same direction. Therefore, the total flux phi T is equal to phi SH plus phi SE. It means that as the load increases, the flux over the periphery get increases, and we know that the EMF generated is directly proportional to flux as the speed is constant. So as long as the speed is constant, the EMF generated in the DC generator is directly proportional to flux. It means that for the DC cumulative compound generator, as load increases, the voltage also increases, but the increase in voltage is small, not similar to the DC series generator, because the DC compound generator is dominantly shunt generator. So it is similar to the shunt generator characteristic, only there is a rise in the voltage, or we can say that there is a good voltage profile for the DC compound generator, cumulative compound generator. Now, if the direction of current in the DC series field winding is reversed, means the direction is reversed, what will happen? The shunt field flux is as it is, only the flux created by the series field winding is opposite phi SE, and therefore the total flux phi T is equal to phi SH minus phi SE. Now here the total flux over the periphery of armature reduces, therefore the EMF generator also reduces, and hence the external characteristic. So this is the external characteristic of DC compound generator. So this is the DC compound generator. One is the over compounded, means it is the series field winding, effect of the series field winding. Here there is a series field winding, but the number of turns are such a design that the voltage should not increase more than the terminal voltage much more. Therefore, it is called as a flat compounded. And whereas for the differential generator, the voltage start decreasing as the load current increases. And now this is the voltage, say, profile for the different type of DC generator. Say this is the no load terminal voltage. This is for the separately excited DC generator. This is for the shunt generator, because in case of shunt generator, the voltage start decreasing. But that decrease in voltage is not much more than 5% or 10% is there. And this is for the DC series field line, DC series generator. Now from this one, we can define the regulation, voltage regulation. So it is the percentage change in the terminal voltage from no load to full load, or it may be at any load condition, at speed is constant and excitation also kept constant. So therefore, the voltage regulation is equal to the no load voltage minus load voltage divided by the no load voltage. So if the load current or load voltage at full load condition, then it is called as a voltage regulation at full load condition. If the current is 50% of its rated capacity, then the voltage regulation is called as a 50% load voltage regulation. No doubt, the voltage regulation must be smaller, means that its value should be small. It may be a 5%, 10%. If the voltage regulation is 20%, it means that the voltage regulation is poor. So if suppose this is the percentage regulation of the generator is 5%, and the second generator, the percentage regulation is 15%. So this is the poor regulation and it is a good regulation. This is the meaning. So this is the some characteristic of DC shunt, series and cumulative differential generators. Now we will see the effect of speed on the external characteristic of DC generator. First, we will take the DC shunt generator. As we know that open circuit characteristic, which is going to plot between terminal voltage versus field current. So this is the field current. This is field current or field MMF, whereas it is the terminal voltage under no load condition, and it is called as a open circuit characteristic, OCC. This is OCC. We know that EMF generated is directly proportional to flux and speed. Now, analysis at constant magnetic flux and variable speed. It means that the EMF generated is directly proportional to speed. This is the effect of speed. We are going to observe the effect of speed on the external characteristic of DC generator. So now this is the open circuit characteristic at some particular speed, say N1 in RPM, whereas this is the higher open circuit voltage. Since the flux is constant, therefore EMF generated is directly proportional to speed. So here this is the field current. We are increasing the field current, and once we are making the flux is constant. So this is the voltage at which this is the open circuit voltage at speed N2 RPM, where N2 is greater than N1. Okay, speed N2 is greater, therefore open circuit voltage is greater. Now, this is the no load voltage E0. We have plotted the no load voltage E0. This is the line. It is E or E0 at no load condition. Now see, at no load condition and speed is smaller, the magnetic core gets saturated. When the magnetic material or the magnetic pole gets saturated, means the flux is strong at lower speed to obtain the required terminal voltage. For the required terminal voltage, the flux should be higher one. So this is the open circuit. This is the OA. Just write OA. Sorry, OB is the flux or MMF or flux to obtain rated voltage. To obtain rated voltage. So the flux density will be more. Now, as the generator is loaded, it will give the armature reaction. But because of the strong magnetic field, the armature reaction will be smaller. Means the effect of armature reaction will be smaller since the pole gets saturated. Let BC is the armature reaction MMF. Armature reaction MMF. And because of armature reaction, the total flux over the periphery get reduces. At that, so this fluxes get reduces, means it is going to reduce the flux. It is going to reduce the total MMF or flux. So this much is the decrease in the magnetic flux. So what is the now MMF? The MMF will be OC is the MMF after armature reaction. After armature reaction, the flux get reduces. And because of this flux, this is the voltage. BC is the voltage. And that BC is the voltage it is going to plot at rated current. Say this is the rated current or some value of the current. We are going to observe this is the load current. So this is the terminal voltage or this is the drop in voltage at lower speed at N1. Now, when the speed is higher, the magnetic flux will be smaller. So this is the magnetic flux. I just rub this sentence. So we will write here. So at lower speed, armature lower speed, field flux or field MMF, or we can write as a flux phi SH or phi SH is OB. Okay, this is OB. At lower speed, field MMF, OB is higher, results in saturation of magnetic flux of magnetic pole. Therefore, armature reaction will be small. Say that is BC. Now, The field MMF is OC. 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 This OC will produce voltage CP. CP. This voltage will going to produce CP. So this is will going to produce CP. So we are getting the terminal voltage at this point. Now at higher speed, at higher speed, field MMF is how much? Field MMF is OC. Field MMF is OC. OC result in lower MMF or flux. Hence, armature reaction MMF or flux will be higher. Why it is higher? Because the armature flux, because the field flux is weakens already, it is a small. So armature reaction MMF, whatever the armature reaction MMF at the same load current will be more dominant. And that's why if you go to the figure, say if the armature reaction is higher one, if it is going to decrease at some same value or somewhat higher value, so this is the somewhat higher, or it may be same, even if you consider the same. So this will be the armature reaction MMF, say A, and we consider it is point D, so it is a AD. And this AD, because of this one, this is going to produce the voltage Q. So here we can say that the AD is the armature reaction, and new value of MMF is O to D. OD is new value of field MMF corresponds to corresponding voltage is A to Q, sorry, D to Q, DQ. The terminal voltage DQ is smaller than CP. So here we are going to plot this one. So this is the point Q, and if you plot correspondingly to the same current, so this is the voltage. So we find that this is the external characteristic. It is the external characteristic of DC shunt generator, isn't it? So the DC shunt generator, if you increase the speed, the terminal voltage get decreases at load condition. So final conclusion, our final conclusion is if the speed is increases at some constant load, at load, the external characteristic will be lower, or the voltage will be lower. So this is the conclusion. Now, if suppose we consider the DC compound generator, say for example, we are considering the cumulative compound generator. So what would be the, in short, we will take, say this is the this is two curves similar to the DC shunt. This is N1 and this is speed N2. So N2, this is N1, this is field current or field MMF. It is somewhere, it is the terminal voltage E0 or E. Now in external characteristic, this is the OCC, open circuit characteristic, and external characteristic. External characteristic. So again, the same terminal voltage, and this is the load current IL, and this is E. This is the EG, and this is E. Okay. Now, at some particular condition, say this is the, for first speed, this is the field MMF required. It is O, B, like similar one. But again, the flux is saturated. And if it is a cumulative compound generator, the flux is going to increase. So here, this is the flux is going to increase. So we will find there is an increase in terminal voltage. So at N1. Whereas for the same armature reaction, the field MMF will be again more. So here this is the earlier MMF or field, this point A. So this much is the point A dash, which is higher. So this is the higher. Same phenomena. This is speed N2. Means it is quite opposite. In case of DC shunt generator, if we will increase the speed, the characteristic is go on decreasing. Means the drop in the terminal voltage is more at same load condition. Whereas for the DC compound generator, the voltage going to increase. So this is the somewhat about characteristic of DC generator. So next time we will start the DC motor.